Welcome to this problem walkthrough. In this video, we'll tackle LeetCode problem number 665, non-decreasing array. We'll explore the problem statement, discuss different approaches, and break down the solution step by step. Let's dive in. In this problem, we are given an integer array called nums, which contains n elements. Our goal is to determine whether it is possible to modify at most one element in the array to make it non-decreasing. Now, what does a non-decreasing array mean? Simply put, it's an array where, for every index I starting from 1 up to n1, the current element is greater than or equal to the previous element. In other words, each element respects the condition nums, id1 equals nums, I. The input to our problem is this integer array nums, which has a length n that can be as large as 10,000. The output will be a Boolean value, true if modifying at most one element is sufficient to make the array non-decreasing, and false otherwise. Let's look at some examples to clarify the problem. In the first example, we have nums equals 4, 2, 3. The output here is true. Why? Because we can modify the first element, changing it from 4 to 1. This gives us the array 1, 2, 3, which is non-decreasing since each element is greater than or equal to the previous one. On the other hand, consider the second example, where nums equals 4, 2, 1. Here, the output is false. This is because no matter which single element we modify, it is impossible to make the entire array non-decreasing. For instance, even if we adjust the first element, there's still a violation further along in the sequence. Now, in the third example, we have nums equals 3, 4, 2, 3. The output is again false. Even with one modification, it's not possible to make the array non-decreasing. This example highlights that the issue might not always be just one isolated violation but can involve multiple conflicts in different parts of the array. Finally, let's consider the constraints to better understand the problem's scope. The length of the array can range from 1 to 10,000, and each element can have a value between negative 100,000 and positive 100,000. This means we need to handle both small and large arrays efficiently. Additionally, edge cases are important to keep in mind, such as arrays with only one or two elements, arrays that are already sorted, or cases where the modification must happen at the beginning or end of the sequence. Since the array length can be as large as 10,000, an efficient solution with a time complexity of O(n) is ideal for this problem. To solve the problem, we first consider the brute force approach. The idea here is straightforward. For each element in the array, we modify it and then check whether the entire array satisfies the non-decreasing condition. This is done by iterating through the array and verifying that for all indices, the relationship nums, id1 equals nums, I, holds true. While this method guarantees correctness because it exhaustively tests all possibilities, it is computationally expensive. With nested loops, one for modifying each element and another for validating the array, the time complexity becomes O(n squared, which makes it impractical for large arrays. On the other hand, this approach uses no additional data structures, so its space complexity is O(1). The trade-off here is clear. While the brute force solution is simple and easy to implement, it is too slow for time-critical applications, especially when the input size grows significantly. Recognizing this limitation, we need a more efficient approach. To address the inefficiency of brute force, we turn to an optimized approach based on key observations about the problem. The first step is to traverse the array and count how many times the non-decreasing property is violated, that is, how often nums, id1, nums, I, occurs. These violations are crucial because if more than one is found, it becomes impossible to fix the array with just a single modification. However, if there is exactly one violation, we can analyze the surrounding elements to decide the best way to adjust the array. Specifically, we examine the relationship between nums, id2, nums, id1, and nums, I. Depending on the situation, we either modify nums, id1, or nums, I, to resolve the violation. Special care is needed for edge cases, such as arrays of size 1 or 2, which are always non-decreasing, and violations near the start or end of the array, where we must avoid accessing out-of-bound indices. The algorithm involves iterating through the array once, identifying and counting violations, and making the minimal adjustment necessary to maintain the non-decreasing property. If no more than one adjustment is made, we return true, otherwise, we return false. This optimized approach significantly improves efficiency. With a single traversal of the array, the time complexity is reduced to O(n). Additionally, since we only use a few variables to keep track of violations and decisions, the space complexity remains O(1). These improvements make the approach well suited for handling larger arrays. However, it does require careful handling of edge cases and precise decision-making about which element to modify. Ultimately, the optimized approach is the preferred strategy because it achieves the best balance between correctness and performance. Unlike the brute force method, which is conceptually simpler but computationally prohibitive, the optimized solution scales efficiently with input size and avoids unnecessary calculations. The key insight driving this solution is the realization that a single violation is permissible and that resolving this violation can be done through a local analysis of adjacent elements. By focusing on this minimal adjustment strategy, we reduce computational overhead while ensuring that the solution remains robust and efficient. In this problem, we need to determine if a given array can be made non-decreasing by modifying at most one element. A non-decreasing array means that for every pair of consecutive elements, the earlier element is less than or equal to the later one. Our task is to return a Boolean value, either true or false, depending on whether this condition can be achieved with only one modification. The key observation here is that the array should have no more than one violation of the non-decreasing condition. If we encounter more than one such violation, modifying just one element will never be sufficient to fix the array. To solve this, we start by iterating through the array to detect any violations of the non-decreasing condition. First, we initialize a variable called modification_count to 0. This will track how many modifications we make. As we loop through the array, we compare each pair of adjacent elements. If we find that the earlier element is greater than the later one, we have identified a violation. When this happens, we increment modification_count. If at any point this count exceeds 1, we immediately return false, because the problem constraints do not allow more than one modification. When a violation is detected, we also determine the best way to resolve it. If the element 2 steps before the current one exists and is greater than the later element, we modify the current element to match the earlier one. Otherwise, we adjust the earlier element to match the later one. This strategy ensures that we make the smallest local adjustment necessary to maintain the non-decreasing condition. Once we have completed the loop, we check the value of modification_count. If the count is 1 or less, we return true, as it means the array was successfully made non-decreasing with at most one modification. The core insight here is recognizing that the problem reduces to identifying and resolving at most one violation. By making local adjustments, we ensure that the array remains as close as possible to non-decreasing without cascading issues further down the array. Additionally, we must consider edge cases, such as arrays with only 1 or 2 elements, which are inherently non-decreasing. Consecutive violations, such as in the case of 4, 3, 2, are impossible to fix with a single modification. Adjustments at the start or end of the array are simpler, as they only affect one boundary element. The algorithm is efficient, running in O(n) time, since we only traverse the array once. It also uses O(1) space, as we only maintain a few variables and modify the array in place. To illustrate how the algorithm works, let's go through an example. For the input nums equals 4, 2, 3, we initialize modification_count to 0. Comparing the first two elements, 4 and 2, we find a violation because 4, 2. We increment the modification count to 1 and adjust the first element to 2, as there is no element before it to consider. Next, we compare the adjusted second element, 2, with the third element, 3. Since 2 equals 3, no violation occurs. The loop finishes with modification_count equal to 1, so we return true, indicating that the array can be made non-decreasing. Now consider another example, nums equals 3, 4, 2, 3. Again, we start with modification_count set to 0. Comparing 4 and 2, we detect a violation. We increment modification_count to 1 and modify the second element to 2 to maintain the condition. Next, comparing the adjusted 2 with 3, we find another violation. This time, we increment modification_count to 2. Since the modification count exceeds 1, we immediately return false. This demonstrates a case where more than one modification is required, making it impossible to transform the array into a non-decreasing sequence within the problem's constraints. The solution class defines a function checkPossibility, which determines if it is possible to make the input array nums non-decreasing with at most one modification. The function starts by initializing a variable modifications to track the number of changes made to the array. It then iterates through the array starting from the second element. For each element, it checks if the current value is less than the previous value. If so, it means the non-decreasing condition is violated. The counter modifications is increment, and if it exceeds 1, the function immediately returns false because more than one modification is required. To decide which element to modify, either nums, I1, or nums, I, the function evaluates the surrounding values. If the violation is at the start of the array or if modifying the previous element, nums, I1, won't create another violation, it adjusts nums, I1, to match nums, I. Otherwise, it modifies nums, I, to match nums, I1. These adjustments ensure the array remains as close as possible to its original structure while satisfying the non-decreasing condition. If the loop completes without requiring more than one modification, the function returns true, indicating the array can be made non-decreasing with at most one change. This solution runs in O(n) time, as it processes the array in a single pass, making it efficient even for large inputs. This is the Java implementation for LeetCode problem number 665, non-decreasing array. The logic mirrors the Python solution, using a counter to track the number of modifications needed to make the array non-decreasing. If more than one modification is required, the function returns false. Key Java differences include explicit type declarations and class structure. The solution checks whether modifying the current or previous element results in a valid sequence, and updates the array accordingly. We start with the input array nums equals 4, 2, 3, and initialize a variable modifications to 0. This variable will keep track of the number of changes we make to ensure the array becomes non-decreasing. The first step is to iterate through the array starting from index 1. At index 1, we compare nums, 1, which is 2, with nums, 0, which is 4. Since 2 is less than 4, the array is not non-decreasing at this point, so we need to make a modification. We increment modifications to 1, then decide how to adjust the array. Since we are at index 1, we modify nums, 0, to match nums, 1, resulting in nums equals 2, 2, 3. Now, the array satisfies the condition at this step. Moving to index 2, we compare nums, 2, which is 3, with nums, 1, which is 2. Since 3 is greater than or equal to 2, no modification is needed here. At the end of the iteration, we find that only one modification was required, so we return true to indicate that it's possible to make the array non-decreasing with at most one change. Here, the input array is nums equals 4, 2, 1, and we start with modifications set to 0. At index 1, we compare nums, 1, which is 2, with nums, 0, which is 4. Since 2 is less than 4, the array is not non-decreasing, so we need to make a modification. We increment modifications to 1, then adjust the array. Since we are at index 1, we modify nums, 0, to match nums, 1, resulting in nums equals 2, 2, 1. Now, the array satisfies the condition at this step. Next, at index 2, we compare nums, 2, which is 1, with nums, 1, which is 2. Since 1 is less than 2, another modification is needed. We increment modifications to 2. However, because modifications is now greater than 1, we immediately conclude that it's not possible to make the array non-decreasing with at most one change. Therefore, we return false. In this example, the input array nums equals 1, 2, 3, 4 is already non-decreasing, so no modifications will be needed. Starting at index 1, we compare nums, 1, which is 2, with nums, 0, which is 1. Since 2 is greater than or equal to 1, no modification is required. Moving to index 2, we compare nums, 2, which is 3, with nums, 1, which is 2. Again, 3 is greater than or equal to 2, so no modification is needed. Finally, at index 3, we compare nums, 3, which is 4, with nums, 2, which is 3. Since 4 is greater than or equal to 3, no modification is necessary. At the end of the iteration, we find that the array remained non-decreasing throughout, with no changes required. Therefore, we return true to indicate that the array is already non-decreasing. The time complexity of the solution is O, n, where n is the length of the input array. This efficiency comes from the fact that the algorithm uses a single loop to iterate through the array exactly once. Let's break this down step by step. First, the for loop runs from index 1 to the end of the array, specifically len, nums, 1, making it a linear traversal. This contributes directly to the O, n, complexity. Inside this loop, we have a few operations that happen for each iteration. Comparisons, such as checking if nums, I, is less than nums, I1, or verifying other conditions like nums, I, equals nums, I2, are constant time operations. Similarly, modifying an element in the array, like updating nums, I, or nums, I1, is just an assignment and also takes constant time, O1. Even the condition that checks whether the number of modifications exceeds 1 is evaluated in constant time per iteration. Since all of these operations are O1, and the loop itself runs n1 times, the overall time complexity is O(n). Now, analyzing the algorithm further, we can consider the best, average, and worst case scenarios. In the best case, if the array is already non-decreasing, the algorithm still needs to traverse the array. Even though no modifications are made, the loop still runs for n1 iterations, and the time complexity remains O(n). In the average case, where one modification is required, the number of iterations does not change, the loop still runs n1 times, with constant time operations inside, so the complexity is still O(n). In the worst case, where multiple modifications might be needed, the algorithm still processes every element in the array exactly once. Once again, the time complexity stays O(n). On the other hand, the space complexity of this solution is O(1), because the algorithm operates directly on the input array without using any additional data structures. Breaking it down, the input array nums is modified in place, meaning no extra space is used to store a copy. The only additional memory used is for variables like modifications, which is just a single integer, and the loop index I, both of which require constant space. As such, the total space complexity is O(1). In conclusion, the total space usage of the algorithm is constant, resulting in a space complexity of O(1). To understand how this compares with a brute force approach, consider the naive solution. In that approach, you would generate all possible arrays after making one modification and check each one to see if it is non-decreasing. This involves O(n) possible changes, and for each modified array, verifying whether it is non-decreasing takes O(n) time. This results in an overall time complexity of O(n squared). Additionally, storing all these arrays would require O(n squared) space in the worst case. In contrast, the optimized approach avoids this inefficiency. By iterating through the array only once and making at most one modification, the time complexity is significantly reduced to O(n). Furthermore, since the current solution modifies the array in place and uses only a few extra variables, the space complexity is reduced to O(1). Mathematically, the time complexity is confirmed as O(n), because the loop runs n1 iterations, each involving a constant number of operations. Similarly, the space complexity remains O(1), because no additional memory beyond the input array and a few variables is required. When tackling this problem, there are several common mistakes to be aware of. First, not accounting for edge cases like arrays with only one or two elements often leads to out-of-bounds errors. This happens when you try to access indices that don't exist, such as nums, I1, or nums, I+1. To avoid this, always check the array length before accessing specific indices. Another frequent mistake is over-modifying the array. Remember, the problem only allows one modification, so changing more than one element violates the constraints and produces incorrect results. Focus on making just one change and ensure it resolves the issue without introducing new problems. Lastly, overlooking the direction of the violation can cause trouble. For example, simply decreasing nums, I, or increasing nums, I1, without analyzing which option preserves the order better might create additional violations later. Always evaluate the surrounding elements to decide the best adjustment. Another mistake to watch out for is assuming that the problem always has a solution. Some arrays cannot be fixed with just one modification, and returning true in these cases is incorrect. Instead, you need to validate the entire array after making your one allowed change to ensure the solution holds. Additionally, inefficient algorithms can become a significant issue, especially with large inputs. Using a brute force approach that checks every possible modification leads to a time complexity of n squared, which is impractical for arrays with thousands of elements. To address this, strive for an O(n) solution by scanning the array once and focusing on a single modification. This approach is both faster and more scalable. For interviews, there are some key insights to keep in mind. A critical pattern in this problem is identifying the first violation of the non-decreasing property. In most cases, resolving this single violation is sufficient to fix the array. It's also essential to ask clarifying questions, such as whether you're allowed to modify the array in place or need to return a new one, and whether duplicate values are permissible. Performing a trade-off analysis can be helpful too. While brute force solutions might be acceptable for smaller inputs during an exploratory phase, interviewers will expect you to optimize for larger datasets. Finally, demonstrating thoroughness by discussing edge cases and alternative approaches shows that you have a well-rounded understanding of the problem. This problem has connections to other LeetCode problems that can help build related skills. For instance, in LeetCode 665, the focus is on making one modification to achieve a non-decreasing array, which is the exact problem we're tackling here. LeetCode 53, maximum subarray, involves scanning an array for specific properties, a similar technique to identifying violations in this problem. In LeetCode 1051, height checker, you practice counting modifications needed to reorder values, which also involves array manipulations. Lastly, LeetCode 198, house robber, shares the concept of analyzing consecutive values under certain constraints. For alternative approaches, a brute force method involves modifying each value one by one and checking if the array becomes non-decreasing. While this is simple to implement, its O(n squared) complexity makes it inefficient for large inputs. A more efficient solution is the greedy approach, where you traverse the array once, identify the first violation, and adjust either nums I1 or nums I to fix it. This method runs in O(n) and is highly efficient, but it requires careful attention to edge cases to ensure correctness. For extended versions of the problem, where more than one modification is allowed, binary search can be a valuable tool. By combining binary search with a helper function to validate the array, you can solve these generalized problems with a complexity of O(n*log k). While this approach introduces additional complexity, it's a powerful technique for variations that go beyond the one modification constraint. Great job! We've successfully walked through the non-decreasing array problem. Remember, practice makes perfect, so try solving similar problems to reinforce your understanding. Thanks for joining, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!